Good morning, everybody. Welcome back. So today what we're doing is what we've done up to now is we've introduced the concept of momentum and the momentum principle, which relates the net force acting on a system to the change of momentum of that system. And from that, we can predict change in position, and therefore we can predict the trajectory of an object into the future. We did this last time with constant forces that didn't change during the interval we were interested in. And we want to be able to do this with forces that vary depending on various things. Often they vary depending on distance between two objects, or they could depend on speed or whatever. And in order to do that, we need to learn to calculate some forces that are more interesting than constant forces and that vary with distance. So that's going to be the focus of today. We're going to talk about two such forces. The first is the force exerted by a spring on an object, a mass in contact with it. That's something that we started to talk about last time, but we'll talk about that more quantitatively. And then we'll actually introduce the first of the fundamental forces that we'll be talking about, the gravitational force, which depends on distance in a different way. So let's start out with a question. And the question is this. We have a system, we don't know what it is, but there's a constant net force in the plus x direction acting on this system for several seconds. And the question is, which of these graphs, 1, 2, 3, or 4, could represent the x component of momentum of this object versus time? An object with a constant net force acting on it in the plus x direction. So you should see a poll. Think about the momentum principle while you're thinking about this. Okay, so this is what you said. And in this case, the answer is actually 4, so the majority is not right. So let's see why not. And why this is, no, the x-axis is time. There's a p sub x is, the x-axis is time, it's labeled on this graph, and so the y-axis is the value of p sub x. Okay, so let's take a look at this and see why this is inconsistent with the momentum principle. So the momentum principle tells us that one way to write the momentum principle tells us that delta p, the change in momentum, p final minus p initial, is the net force acting on something times the time interval. And that means that the change of momentum over this time interval is equal to the net force acting on this object. Now this is a 3D vector, but as we know, a vector equation is really 3 equations, one for each component. So we'd have the change in the x component of momentum over time is equal to the x component of the net force. Now, if this is a graph of the x component of momentum versus time, then, and the force is constant, that means that this quantity, delta p sub x over delta t, is constant. If this is constant, this is also constant. What is this quantity, delta p sub x over delta t? What is the meaning of that quantity? No, it's not momentum. It's the rate of change of momentum with time. No, it's not the net force either. So remember that this equation here is a causal equation. What this tells us is not that these two things are the same. It tells us that the net force times a time interval, the net impulse, causes a change in momentum. So this is cause and this is effect. So they're not the same thing. Yes, the slope. So this is the slope of this line. Now, so the slope of this line of P sub x versus t, the slope of this line gives us dpx dt, and that should be equal to the net force. So if the net force is 0, the slope of this line should be 0. And so this says, so for graph 1, the slope is 0, so f net x is 0 here. Now, okay, in a trivial sense, a 0 net force is a constant net force, but that wasn't the intent of the equation. Yes, Seth, that's right. It's change in momentum over time change, and that is the slope of the graph, right? So let's think about what these other graphs would tell us about the net force in the x direction, the x component of the net force acting on these things. So graph 2, here the slope is less than 0. So that tells us that the net force in the x direction, the component of the net force in the x direction is negative. So that says there's a constant net for the slope isn't changing, it's constant, but this says there's a constant net force in the minus x direction. So now graph 3, we have the momentum here. So this is px here. The x component of momentum is increasing, but is it increasing at a constant rate? So it's not. So dpx dt is not constant. So the momentum is changing, but this actually indicates it's getting bigger in the plus x direction, but this indicates that the net force is changing because the slope of this graph keeps changing. So here is the only graph, P sub x versus t, where the momentum, the slope is a positive number and it's constant. So here slope is greater than 0. So this tells us f net x is greater than 0. It's positive. And the slope is constant. So f net x is constant. Now, Seth asks about acceleration. Remember that the definition of acceleration is the rate of change of velocity versus time. And so acceleration in the x direction would mean the rate of change of v sub x versus time. And this is going to be directly proportional. So the rate of change of p sub x versus time is directly proportional to the rate of change of v sub x versus time, since momentum is approximately mvx, and we're assuming that we're going much slower than the speed of light, so that's a good approximation here. And so, in fact, in any of these cases where p sub x, the momentum is changing, that means the velocity is changing, and that means that the thing is accelerating. So graph 2, 3, and 4 also all show an acceleration. The only one that shows zero acceleration is graph 1, because the slope is constant, the momentum is constant, and it's not changing. Okay, so what does it mean for the value of p sub x to be negative here in graph 4? So why is p sub x negative here? What does that tell us? So let's think about a situation here. If we had, and what would a situation be if p sub x was negative? It would mean the momentum would look something like this, -3. Let's keep it simple. We're moving in only one direction here. 0, 0 kilogram meters per second. It just means that the object is moving in the negative x direction, and as Marcos says, that must mean that the momentum is in the opposite direction to the force. So the object is moving this way, but the force acting on it is in that direction. And what is that force doing? It's slowing it down, isn't it? That's exactly right, Claire. It would mean it's slowing down. What would it mean if the graph of p sub x versus time did this? So it started out like this and it went up like that. What would that tell us about the motion of the object? Yeah, that's right, Matthew. It means that it changed direction. So here we start out with momentum in the minus x direction. So the object is moving to the left, but the value of p sub x is getting smaller and smaller and smaller and smaller, and it gets to 0. So the object moves to the left, but it's slowing down. And finally, it comes to a stop, and then there seems to be a net force still acting on it, so it actually turns around and starts going the other way and starts speeding up. So we have to look at the slope of a line of a graph like this to tell us how something is changing. And so that's what forces do, is change things. So we're interested in change. And we look at the sign of the value to tell us the direction in which something's going. So let's go back to talking about forces and what forces can do. We'll see an example in the next thing we look at, an example of forces that can change speed and direction. So one message from this exercise, by the way, is that force and momentum are not always in the same direction. And what we've got here is clearly in graph 4 a situation where momentum is in one direction and force is in the opposite direction. And what's the force doing? It's changing the momentum by slowing it down. And we'll see that that a spring force can do this too. So we started talking about this last time, but we didn't get very far. So let's review this. We're interested in the force exerted by a spring on an object in contact with the spring. And this could be in a number of different orientations. So we could have a spring standing vertically on the floor and an object on top of it. We could have a spring hanging from the ceiling and an object suspended from it. We could have a spring attached to a wall and extending horizontally, and an object sliding on a low friction surface here. And in any case, if we either stretch the spring or compress the spring and then let the object go, it's going to oscillate, right? It's going to move up and down or back and forth or whatever, depending on. And so what we need to do in order to model this motion is we have to calculate the force exerted on the force by the spring on the object. Now, the two forces that we're going to talk about here today have two characteristics. We're also going to talk about a gravitational force where we have some massive object interacting with some other massive object, and the big object exerts a force on the little object and vice versa. And in all these cases, there are two things to keep in mind. One is going to be that the force is not constant because it depends on distance. In the case of the spring, how much the spring is stretched or compressed. And in the case of gravitation, how far apart these two objects are, the center to center distance. And it also, the direction, in order to get the direction, so this is really the magnitude of the force. The direction of the force depends on a unit vector along the line, pointing along the line between these objects, and there may be a minus sign. So in both cases, we're going to need to know something about distance, and we're going to need to know something about direction. We're going to capture this direction with the unit vector. So last time we talked about, so I'm just going to write down the expression for the spring force as a vector, and then we're going to go through it and take it apart and see what it actually means. So the spring force, so I'm going to call it F spring. This would be the force that one of these black springs exerts on the green object attached to it, is equal to, there's a constant, and the constant is called K sub S, times a quantity S for stretch, times a unit vector L hat. So what do these things mean? The constant K sub S, it's a positive It has units of newtons per meter. It's called the spring stiffness. And it just means how hard it is to compress or stretch the spring. So if the spring is very soft, you don't have to exert much force to compress it or to stretch it. But if the spring is very stiff, you have to pull hard. And so it means how many newtons of force would you have to exert to stretch the spring by a meter? This quantity S is the stretch of the spring. And we defined that last time as the current length of the spring minus its relaxed length. So this is the spring length when it's relaxed and nothing is touching it, relaxed length of the spring. And this is its current length. And you can see that stretch can be positive or negative. Because if the spring is longer, if it's stretched, it's going to be a positive number because it's longer than its relaxed length. But if it's compressed, it's shorter than its relaxed length, so that's a negative number. And then this is a unit vector in direction from the fixed end to the moving object, or to the object that's experiencing a force. Case of S is never negative. It's a positive constant. This is a minus sign. So case of S is a positive number, and the minus sign is part of the equation. We'll see where it comes from. We'll see why we need a minus sign here. So the stretch, as we talked about last time, is, let's consider a spring standing on a surface. If it has some relaxed, if there's nothing on it here, this is going to be its length L0. And if we stretch it to some new length L, then this distance here is the stretch. It's the difference between its current length and its relaxed length. If we compressed it to some other new length, L2, then the stretch would be equal to that distance, and it would be less than 0. Now, the unit vector is a vector that goes from it points to the end of the spring that's exerting the force on something. So in the situation we've drawn here, let's draw a situation where we've got a spring. Here's our floor. This is attached. We have a block sitting on top of the spring. The vector L is defined as going from the fixed end of the spring to the mass. And therefore, the unit vector L hat is just going to be a unit vector in the direction of the vector L. If we have a spring hanging from the ceiling, the vector L would go from the fixed end to the mass, and so L hat would be pointing that way. If we had a spring, a horizontal spring, then we'd have the vector L, and therefore L hat going that way. And notice that it doesn't matter whether the spring is compressed or stretched, since the unit vector L is always pointing in the direction from the fixed end to the moving end, its direction is going to stay the same no matter what's happening to the spring. Now, what's the deal with this minus sign? What's going on here? Why is there a minus sign here? Well, let's consider a situation where here's our relaxed length of the spring, L0, and we've compressed the spring and we've put a block on top of it. Now, in what direction is the spring going to be exerting a force on this block? Up, exactly. So we know that the force needs to be up. So let's see what this equation tells us. So let's say the spring stiffness is, let's say, let's say the spring stiffness is 5 newtons per meter. And let's say that that distance is 3 centimeters. Then the y component of the force, we need the spring stiffness times the stretch times, or actually, let's write the force as a vector. The force is going to be the spring stiffness, which is 5 newtons per meter, times the stretch, which is the current length minus the relaxed length. So let's say the relaxed length is 10 centimeters, and so this current length would be 7 centimeters. So this would be 7 times 10 to the minus 2 meters minus 10 times 10 to the minus 2 meters. And the vector L hat, by inspection, it's pointing up, right? So L hat points up. So we can just write, we know what the unit vector pointing up is. It's just 0, 1, 0. And if we work this out, we're going to get 5 times a negative 3 times 10 to the minus 2 meters times 0, 1, 0. And that would give us a force in the minus y direction, okay, because of this negative stretch. So we need the minus sign to give us, to make the force go in the correct direction. So we're adding, that's where that minus sign comes from. Now let's see what happens if the spring is stretched. Does that still give us the right answer? So let's consider up here, if we have the spring, the mass is oscillating up and down. And now let's say the length of this spring so the length is 14 centimeters. So let's try that. The force is equal to, this is compress. It's equal to minus 5 newtons per meter times, now we have 14 times 10 to the minus 2 meters minus 10 times 10 to the minus 2 meters times 0, 1, 0. And that gives us a minus 5 newtons per meter times a plus 4 times 10 to the minus 2 meters, 0, 1, 0. So that tells, so this says that the force will be in the minus y direction because with this minus sign here. So this is plus y. This is going to be in minus y. Is that right? The spring is stretched. What direction should it be exerting a force on the block? Yeah, that's right. It should be trying to pull the block back down, forced by the spring. Should be. And so, in fact, we get the right answer, but we need this minus sign to get the right answer. So now we have all the pieces. The spring force is equal to minus this positive constant, which is a spring stiffness, times the stretch, which could be positive and it could be negative, times L hat, the unit vector that points from the fixed end to the. It's one equation and it works for both, because notice that in the case where the spring was compressed, the stretch was negative. No, the unit vector points from, the vector L points from the fixed end to the moving end. So no matter what, doesn't make any difference whether the spring is stretched or compressed. That direction doesn't change. Why is there a minus sign in the compression equation? It's one equation and it works for compression or stretch. So if here the stretch, in the case where it's compressed, here the stretch is negative. And so if we didn't have that minus sign, imagine that this minus sign weren't here, then we'd get, here, let me make a little more space. Let's work this out. So we get a minus 15 times 10 to the minus 2 newtons times 0, 1, 0. And that gives us a force of negative 0.150 newtons, but that's in the wrong direction. We said that when the spring was compressed, the force had to be up, but without that minus sign, we get a force that's down. So we need that minus sign to give us a force in the right direction. So that's just part of the force equation. So Isaac, does that make sense? Okay. So Morgan says, if the spring was hanging from the ceiling, would the unit vector then be negative 1, 0, 0, negative 1, 0? And the answer is yes, absolutely. Let's see, here's our picture with the spring hanging from the ceiling. And so the vector L starts at the fixed end and it goes to the man. I'm just drawing it beside it so it's not as messy. And so the unit vector L then points down regardless of whether the spring is stretched or compressed. So here's a spring whose stiffness is 30 newtons per meter. And the spring is 12 centimeters long when relaxed. Now remember, we have to convert to SI units here, so that's 0.12 meters. We push on the spring, compressing it, so it's now 10 centimeters. So the question is, what is the vector L? Not the unit vector, but the vector L. So L hat is a unit vector in the same direction as L, but this is actually asking for the vector L. So think about how L was defined. Where does it start? Where does it end? Okay, so what this looks like is confusion. So what did we say about the vector L? Goes from, where does it start and where does it end? Yep, that's right, exactly, Julian. Fixed end to moving end. Yes, yes, you're exactly right. So let's draw it on this figure. So we want the compressed spring, so the fixed end is attached to the floor here, and the moving end is the free end. So that's going to be the vector L. Okay, right. Okay, so let's just try this again. So what is that vector? We have the usual coordinate system. We've got X, Y, Z out of the page. So let's try this again. Okay, I think I see what you're asking, Melinda. You're saying are we talking about, the vector L reflects the current situation, and so as the mass moves up and down, the vector L will change. So we are indeed asking about the current instant here. Okay, so that looks better. The direction, and how do we get this? The direction of L, as I think Alexander said, so L is going to be equal to the magnitude of L times L hat. And the magnitude of L is just going to be the length of this spring here. So that's 0.1 meters times L hat, which is indeed a unit vector in the plus y direction. So that's times 0, 1, 0. So that's going to be 0.10 meters. So if you answered 1, what question were you actually answering? Someone who picked answer 1, what is that actually equal to? So this is L. That's right. So this is actually equal to L hat. That's the unit vector. Okay, good. Let's see if we can figure out what a stretch is. So here's the situation. We have a spring with given spring stiffness. Its relaxed length is 12 centimeters, 0.12 meters long. You push it down, so it's now 10 centimeters, so exactly the same situation as before. But now the question is, what is the stretch? What is the value of the stretch S? Okay. So 4 is indeed the correct answer. And let's see why. The stretch is equal to the current length minus, the current length minus the relaxed length. Notice that the current length is actually the magnitude of this L vector minus the relaxed length. So the current length is 0.1 meters, and we're subtracting from it the relaxed length, which is 0.12 meters. And so in fact, we get a negative 0.02 meters for the stretch. So stretch has a sign, and you have to calculate it correctly. If you follow, the equation just tells you how to do it, and if you just do it and don't try to second guess it, you're going to get the right answer, okay? Okay, so that's good. So let's put this all together here and calculate the force. So we had the vector L was the vector 0.1. Or actually, we got L hat was the vector 0, 1, 0. We just calculated the stretch. We have the spring stiffness is 30 newtons per meter. So the force on whatever's pushing down on this thing, your hand, that's your hand. The force on your hand by the spring should be negative 30 newtons per meter times a negative 0.02 meters times the unit vector 0, 1, 0, which is going to be equal to 0. We have a negative 30 times a negative 0.02. So that should be 6 newtons. Now, does that make sense? Is it in a reasonable direction? That says that the force should be pushing up. The spring is exerting a force upward on your hand. And that makes sense because that's the way it should be. So we did need that minus sign. That minus sign helped us get the right direction. 0.6, yes, it should be 0.6. So, okay. So we calculated a spring force. Now, what can we actually do with that? Well, we could use the spring force to predict momentum, for example, and momentum to predict position. So if we calculated the spring force many times, so suppose we start by pushing the block down, so the spring is compressed, and then letting it go, it basically should oscillate up and down. It should go up and then down and then up and then down. Now this calculation is a little complicated because the net force isn't just the spring force, right? There's a gravitational force on the block too. But that's okay, we can put that into our calculations. So let's see what happens if we do that. So what I want to do is show you a GlowScript program in which we actually do that calculation. So here's a VPython program that does that calculation. We'll talk about what that calculation looks like in VPython in a moment. So we have a So the vector L would go from the base of the spring to the center of the mass. And what we're going to do is this iterative update of momentum here. So what we're going to do is calculate the spring force, then plug that into the momentum principle along with gravitational force to get the net force acting on the block. Use that to update the momentum of the block. Use that to update the position of the block. And now with blocks in a new position, so we have to calculate the spring force again. So here's what we're going to do. Excuse me, there's the spring force. And that's the net force, actually. The gravitational force is down, but the spring is compressed enough that it's exerting a big upward force, so that's the net force. So that's going to change the momentum. That's going to give us a momentum in the plus y direction. We're going to use that momentum to estimate the average velocity, and the block will move up. And this is a graph of y versus t. So the x-axis is time. You can see we're taking steps of 0.1 second. And the y-axis is height above the floor. Okay, so now we have a momentum upward. And we're going to calculate the force again, the net force again. Now the spring is no longer compressed, or not very much anyway, but the combination of the spring force and the gravitational force gives us a small net force in the downward direction. So that's going to decrease the upward going momentum. It may not completely reverse it, but it's certainly going to decrease it. Yep, there, the momentum. So the block is still going up, even though the net force was down. The block had enough momentum going up that the net force slowed it down, but didn't actually bring it to a stop. And so then it's going to move up again, but a little bit less. You can see that the y displacement is less here. And now we're going to calculate the net force, and now the net force is down probably because the spring is actually stretched at this point, and so it's pulling down in the same direction as the gravitational force. And so now this actually added to the old momentum gives us a downward momentum, so the block is now going to move down, which it does. Now we've got this downward momentum, we have a downward force. Not as big because the spring isn't stretched as much. So this increases the momentum down. And now we have a bigger momentum down. But now we're getting to compress the spring again. So the net force is starting to be up again. And that decreases the momentum almost to zero. You can see a very tiny blue blob here. The momentum is small but non-zero, but it's still down. So it's going to go down just a little teeny bit. And now we get a force up. That changes the momentum to be up. Now there's a net force, small net force down, so the momentum is still up, but now the momentum's up, but we have a net force down. And so indeed we are starting to get these oscillations. Is this harmonic motion? For an ideal spring, it turns out to be something we would call harmonic motion. I think the most important thing about this is what we'd call it periodic motion, because it repeats. So every period, let's see, from where it was at a peak to where it's at a peak again, we went from 0.2 seconds to 0.7 seconds, so it seems to have taken half a second to get there, so it has a period of about half a second. Okay, so we can just keep doing this for a long time, right? Now, what would improve this calculation? Does the spring mass really move in these jerky, more time steps? We have gravity in here. Gravity's taken into account. We've got the gravitational force in here in this program, and I can show you that. So if we just take, decrease delta t, that's right. So let's see what happens if we decrease delta t. So we're going to make delta t smaller than 1/10 of a second, something like 100th of a second. And now note that the momentum, one lesson again is that the momentum is not always in the direction of the net force. And we get that from the momentum principle, that the momentum at any instant depends on the momentum an instant before as well as the net force that was acting on it. And now we get a much smoother up and down oscillation. We could take air, so Marco's suggestion of taking air resistance into account is a good one, and you will probably do that in a program that you write later on this semester. So you'll have a chance to actually look at that and see what different kinds of damping, air resistance or viscous friction or whatnot, what effect that has on a motion. Okay, so let's take a minute and just think about what the code to do that must have looked like. And I want to talk about how we would do that on a computer, because you don't want to keep doing those calculations by hand. So basically what we need to do is the same thing. We need to calculate the spring force. We need to get F net is equal to the spring force and plus the force by the earth, the gravitational force. We have then we have P final is P initial plus F net delta T. We have R final is R initial plus F net delta T. Sorry, not F net, P average. So P final over the mass times delta T. And now we have a new position, and so the spring force is going to be different, so we have to do it again. Now, calculating the spring force has a lot of pieces, so that would be our loop. And the spring force has a lot of pieces. So let's actually give ourselves a little room to write down what we did here. So to calculate the spring force, what we need to do is find L, which is the vector from the position of the block to the block position of the floor, or the end of the spring. And then we get L hat, which is just the L over the magnitude of L. The stretch is the magnitude of this vector L minus L0, the relaxed length, and we need the spring force is minus K sub S times L hat. So that all goes in there. So our calculations would be something like this. So basically, let's assume that we have in our program something, the mass is called a block, and it's a box, and it's got a position, which is a vector, etc. And we have something representing the floor. It's another box, and its position is something. So this calculation we could do is, this is block, so L can't, unfortunately there's no way to like symbolize a vector in Python. That would be nice if there were, but we could make it block dot position minus floor dot position. So that's the relative vector between the block and the floor. Now, L hat remember that we can calculate it by taking the magnitude of L and and dividing that into the vector L, but actually remember there's actually a VPython function to do that. So we can just say hat of L. And we could calculate the stretch as the magnitude of L minus the relaxed length, which we must have defined somewhere up there. And so the spring force would be minus Ks, some value we've already defined, times the stretch times L hat. And so all of that is calculating the spring force. And then we'd have the block's momentum is its old momentum plus the spring force plus the gravitational force times delta t. So up here we would have wanted to calculate, so we need a gravitational force. Maybe we should just actually put it in here. We'll put it inside the loop even though it's constant. So the gravitational force is going to be a vector 0 minus the mass of the block times the value of g, which we've defined up here. So we've defined g equals 9.8 newtons per kilogram, Ks is whatever it is, 30 newtons per meter. And that's a momentum update. This is now the net force. And now we can update the block's position. It's the old position of the block plus the momentum over the mass times delta t. And we would need some kind of loop conditions, wouldn't we? So we'd probably want to put this block of code here. In a loop while, I don't know, time is less than 10 seconds or something. So we need to initialize the time as 0, and we need a delta t is 0.01 seconds, something. And we'll put in a rate 20 just to see it happen. And that would actually enable us to do the calculation. And that's basically what that program I showed you does, actually. So the whole point of going through this calculation of getting the spring force is to be able to do something to predict the motion of this oscillating block open-endedly into the future. And a nice feature of this is that since we've gone to all the trouble of doing this, writing a vector equation, this exact same program would work even if we stretched the spring this way and had the block there initially. Now you can imagine that the trajectory might be kind of interesting. It would not only go up and down, but it would move sideways as well. And so it's just a matter of where we start the block as to how that calculation actually plays out. So there's some things that are called initial, oh, we better initialize the momentum too. So we want here P equals vector 0, 0, 0. So the thing, so if we have different initial conditions, a different initial momentum, maybe the block is moving a different position, we get different motion. That's how that program actually works. Okay, so we actually don't have time to do the gravitational force, but that's okay. I thought we might not. And I think our conversations about the spring force were useful and interesting. How can you calculate the maximum force a spring can take? Well, that's hard to calculate because it depends on the properties of the particular object and the material it's made of. So it's absolutely true that if you take a real spring and you stretch it and you stretch it even more, pretty soon what you've got is a straight wire. It's not a spring anymore. And then if you stretch it even more, it'll eventually break. And that depends on what it's made of and how thick the material is and whatnot. So that's a very individual thing, which is, and also we've been talking about ideal springs. So when you compress a spring, what's eventually going to happen is the coils are going to come in contact with each other and it will stop. And then what you get is something like, that's really more like a solid cylinder, and that's much harder to compress. So it would have a completely different spring stiffness. So the calculation here is within reasonable limits of sort of ideal behavior here. We're assuming that we're not breaking the spring and we're not having the coils hit each other. But it's a good question, and predicting that would actually be a hard problem because it would involve having to know about the material and the shape and various things like that.